Okay, so we're going to take a look at our next topic, which is Monte Carlo integration, or Monte Carlo estimation. Okay. And so we might have some kind of function, all right, or some kind of random variable. So we'll say x is a random variable. From some distribution. Okay. And if we apply a function to x, a reasonable question will be, what will be the expected value of the function, okay? And just keep in mind, important, that the expected value of a function applied to x is not the same as the function applied to the expected value of x. Okay, so here's a simple example. Okay, so let's say my function of x is just, you're going to take a function and you square it. Okay, and we'll say, so we'll say let f of x be x squared, and let x come from the standard normal distribution. Okay, so what's the expected value of x? If x is standard normal. It's not a trick question. It's 0. Thank you. Okay. All right. So if I apply f up to the expected value of x, what would I get? I would get 0 squared. I would get 0, right? But what is the expected value of f of x? This is something different, right? What is f of x applied to the random variable x? What will that produce? This will produce a chi-squared random variable, right? If I take values from the standard normal and I square them all, I'm going to get the chi-squared distribution with 1 degree of freedom. And then, and so the expected value of f of x is going to be the expected value of a chi-squared with a 1 degree of freedom, which is 1. Okay, and so it's a reasonable question to ask. What is the expected value after I apply a function to a random variable? Okay. Okay. So conceptually, does this make sense? Okay, and so the what would the Monte Carlo approach be? So how would we, well, if you did 100b, I don't know, did you have to calculate the expected value of the chi-square distribution. Okay, maybe you'd use like method of moments, or I don't know, something else, right? Maybe you could do integrals and stuff, but you know, you'd have to do math, right? And the whole point of this class is let's avoid math, and we're going to do the Monte Carlo approach. We're going to have the computer generate random values for us, and let's figure this out. That's what we're doing, right? So okay. So what do you think would be a good Monte Carlo approach? So I'll say expected value of chi-squared. This is, you know, we'll say from 100b, you know, maybe method of moments or something. Something mathy to get the expected value. Okay, the Monte Carlo approach to estimate the expected value of f of x. Okay, and here f of x again is x squared, and x is standard normal. All right, what would we do? What do you think? Well, this is it, okay? First, we're going to generate a bunch of random x's, from the normal distribution. Okay, then we apply the function f of x, x squared, to all our random values. Okay, and then take the mean of the squared values. Does that make sense? It's simple enough, right? This is the Monte Carlo approach. We're going to just do this, and so here I'll just demo it really quick. Man, R is struggling to start up. Here we go. Right. Okay. I don't know what's going on here. Ah, shoot. All right, let's try this again. All right, so we'll say x will be R norm. I'll ask for 100,000 of these random normal values, and then I'm just going to ask for the mean of x squared. Okay, and we get 0.998, which is quite close to the theoretic value of 1. Okay, so again, Monte Carlo approach, you're only going to get an estimate. Okay. You're not going to get theoretic answers because we're not doing any kind of theoretical math. So this is it's not too bad. Okay, this is a decent estimate of what it should be, right? So we get, this is our estimate. Okay, so it's pretty good, I think. Okay. All right, so this is the general idea here. Okay. Oh, and I guess I've used the. Let me go back. I'm going to go change all of these f's to, well, it's fine. I probably should have written h's. Okay, here's our generalized form. Generalized form of Monte Carlo estimation. Okay, we're going to say x is a random variable with PDF f of x, okay? We have a function of interest h of x, okay? And we want, let's say we want the expected value of h of x applied to the random variable x. Okay? And so we're going to write the expected value over the random variable that's defined by f of the function h of x. Okay, so this is the expected value of h of x over the random variable defined by f. That's how we might read something like this. Okay, this is going to be equal to the integral of what? We're going to say h of x times f of x dx, okay? And this is over the domain of x, okay? So this is integral over the domain of x, okay? And that's the expected value of h of x over the random variable defined by f is equal to the integral over the domain of x of h of x times f of x dx. Okay? So there we go. All right. So all right. So let's do a simple case. Okay. So we'll say we have some function h of x. Okay. And we want to know the average value of h of x over some interval a to b. Okay, so here go from a to b, and we have this function here. Okay. Yeah. Let me just actually I don't even want that. Okay. We just want to figure out what's the average value of this function. Okay. So I don't know, what is that? Something around here. This is kind of the whoa. Average value of h of x over the interval. So just this kind of line right along there. Okay, how would we go about doing this? All right. So what we can do is we can just say let f of x be a PDF, which is kind of going to be the uniform distribution between A and B. Okay. So we're going to just say f of x is going to be equal to 1 over a minus b. Or I'm sorry, b minus a. So we'll say f of x is going to just be the PDF, okay? And then we can say the expected value of h of x over the integral f will be the average value of this function over the interval, right? Okay, so the average value, this will be equal to the average value of the function over the interval. Okay, so we'll use our Monte Carlo estimation equation. We've got the integral over the domain of x of h of x times f of x dx, okay? And we have f of x being b minus a. So this becomes the integral of h of x times 1 over b minus a dx. And this will be on the interval a to b, okay? And 1 over b minus a is a constant, so we can just pull it out of the integral, and we get 1 over b minus a of that. So this is what we have here. Okay, and so the Monte Carlo approach how do we do this Monte Carlo approach to estimate, to get an estimate of this value? Okay, so we have a PDF f of x, okay? So we're going to, so we will estimate the expected value by 1, okay? Generating a bunch of x's from uniform a to b, right? So we're going to generate a bunch of x values, and then we're going to just apply the function h of x to the random values of x, and then we take the mean after applying the function. Okay, this is known as the Monte Carlo estimator. Which we'll call h bar sub n. And this is equal to 1 over n of h applied to x super I which is going to be 1 over n. I'm sorry, I'm missing a sum here. Equals 1 to whatever it is. Okay, so basically x super I is a value, random value from the PDF of x. Okay, so you generate a whole bunch of these things, and then you apply the function, and then you take the mean. So, you know, whatever your function is, it works out, right? Okay, so for example, let's say h is going to be the function sine of x, okay? And let's say we do the interval from 0 to pi. All right, so let me just do s will be a sequence from 0 to pi, and we'll just do 1,000 of these values. Okay, and then I'll plot s versus h of s type equals O. What's going on there? Did I mess something up? How do I do sequence? I forgot. Okay, from 0 to pi, a length out. Okay. Length dot out. That's what I need. Okay, whoa, too much. All right. Oh, sorry. Let's do 0 to 2 pi. 0 to 2 times pi. Okay. Okay. So what's the mean value of this function over this interval? It's 0, right? It's no surprise there. Okay. All right. So this is what we want. Okay, and we want to figure out the average here. Okay. So how can we do this? The Monte Carlo way, well, we're going to just generate a bunch of x's on our uniform, and let's do 100,000 of these things, okay? And then and I'm going to just go ahead and say from 0 to 2 times pi, all right? So I get a bunch of random x values, and then I apply the function h of x to all of these things. And then what do? I take the mean of it. All right, so if I ask, you know, what's the mean of x, that's going to be 3.14, which makes sense, okay? But here we're going to ask for the mean of h applied to x. And I get something close to the real thing. Not exactly 0, but I get negative 0.0009, okay? So this would be kind of our estimate of what is the average value of the function over the interval. Okay. Likewise, if I would just wanted to figure out what's the average value on 0 to pi, okay, I would say, okay, x is going to be our uniform. We'll ask for 100,000 values on the interval 0 to pi. And then I just ask, what's the mean of applying the function h to x? And I get the value 0.63555, okay? Okay, which I think is approximately equal to 2 over pi, I think. So the true value is 2 over pi. If you do the integral, okay, you'll get 2 over pi. And so we get a value that's kind of close, not exactly the same, but we get something kind of close to the true value doing Monte Carlo estimation. All right, is this okay? So this counts as Monte Carlo estimation. We're estimating, you know, something after we apply a function to it. Okay. All right. Okay, so let's say what if I give you a function h of x is equal to x squared, all right? And I say, you know, what is the average? What is the value of the integral over the interval 0 to 5? Okay, so this, what we want is the value of the integral which goes from 0 to 5 of x squared dx, okay, which is going to be 0 to 5 of h of x dx. Okay. Now this is a simple enough integral that you guys can do it by hand or even in your head, okay? But what can we do to approach this the Monte Carlo way? Okay, so you know the function from 0 to 5 looks like this, okay? And we want to know the value of the integral. So I propose that the value of the integral is equal to the so if I find the average value is equal to the average value times the width of the interval. Okay, so if I can find the average value, the expected value of h of x, and I'm over the interval, I can multiply that by the width of the interval to get the total area. Does that kind of make sense? So we're going to just, so rather than calculating this shaded area underneath the curve, I'm going to say, well, let's just take the average value over the entire thing, and we'll find the shaded area of this corresponding rectangle. Okay, so then so we can estimate I as the width of the interval, which is going to be b minus a, times the expected value of f times h, expected value of h of x over the interval f, or over the PDF f, and we'll let f be the uniform on a to b. Does that make sense? Okay, so what would the Monte Carlo approach be to get the expected value Okay, what would this be? Okay, so first of all, x has PDF what? So x comes from the uniform. What is my interval for the uniform? It goes from 0 to 5. Okay, so x has PDF 1 over 5. Okay, so X has this PDF, all right, and okay, and then how do I get the average value of h of x? So the expected value of f of h of x is going to be the integral of x times h of x times f of x dx. Okay, so this is the integral of x squared times 1 over 5 dx. All right, so I got 1 over 5 the integral from x squared dx. And the way we get this to estimate what do we generate? We generate a bunch of x of i's drawn from uniform 0 to 5, and then we square all of them, and then what do I do? Take the mean. All right, so this will give me, so this gives the Monte Carlo estimator. Monte Carlo estimator, all right, which is h bar sub n, which is approximately equal to this. And then to estimate I, I is equal to the width of the interval, b minus a, times the expected value of h of x over the interval. So here I would have b minus a times my Monte Carlo estimator, and I would just get 5 times h bar of n. Okay. So let's clear this out. We want to generate uniform values from 0 to 5. No, our unif, I need like 100,000 of these. Okay, 10 to the 5th. Okay, so I generate a bunch of random x's, and then what do? My h of x is to square them, right? So I can just say h of x is take each of our x values and then we square them. And then what? I take the mean of h of x, okay, and I get 8.3244. Okay, so I have h bar sub n is equal to 8.3244 from R. And so my estimate of I is equal to 5 times that. 5 times the mean of h of x. 41.622. Okay, and then let's just, so this is our estimate. Maybe I'll write I hat, okay. So we'll compare to the actual value of the integral of 0 to 5 of x squared dx. And so this gives me x to the 3rd evaluated at 5 and 0. And I would get 5 cubed over 3 minus 0. So 125 divided by 3, which gives me 41.667. 41 point, yeah. So this is our estimate, 41.622. The actual value of the integral is 41.667. Okay, so we can use Monte Carlo estimation to also estimate values of an integral. Okay, you just use the estimation to estimate the average value of the function over an interval, and then to get the value of the integral over the interval, you multiply it by the width of the interval. Okay, so Monte Carlo integration goes like this. Okay, use Monte Carlo estimation to estimate the estimate the average value of the function over an interval. All right, and so and then use a uniform PDF, and then multiply the average value, estimated average value, by the width of the interval. Okay, so far all of our PDFs have been uniform, but that's not necessarily the case. Just like the very first example before we did any math was, what if our PDF came from something that wasn't normal, right? And so I guess we'll take a look at it on Monday, but we can extend or we can use Monte Carlo estimation even when our PDF is not uniform. Okay, I've posted up homework 2. That's available online. You guys can start taking a look at that. And I think we've covered pretty much the core of what you need to accomplish homework 2. So you guys, I recommend go ahead and taking a look at that. Okay, have a great weekend, and we'll see you guys on Monday.